Okay, 2018 paper 2, Edexcel A-level maths. Let's go straight into it. Question 1. We're told that g of x equals 2x plus 5 over x minus 3, and we have a restriction on our domain that x must be larger than or equal to 5. Part of this question, nothing too tricky. We have to find g of 5. What does that mean? We have to plug 5 into our function g, and then with that result, plug that back into our function g. So first things first, let's find g of 5. G of 5, so what do we have? We have 2 plus 5 over x minus 3, so we're going to have 2 times 5 plus 5 plus 5, sorry, not plus 3, plus 5, 5 minus 3. That is going to be 2 times 5 is 10, plus 5 equals 15 over 5 minus 3 is 2. So we have 15 over 2. Now we have to plug that result back into our function g. So we have g of 15 over 2. Plug it in. So we're going to have 2 times 15 over 2 plus 5 over 15 over 2. Take away 3. So what is that? 15 over 2 times 2 is just 15. 15 plus 5. So on the numerator, we're going to have 20. And looking at the denominator, we have 15 over 2, which is 7.5. Take away 3. That's going to be 20 over 4.5. Just to get rid of that 4.5 on the denominator, let's multiply the top and bottom by 2. So we have 40 over 9. That is your answer to part A. Nothing tricky in part A. Moving on to part B, we have to state the range of G. So when we're thinking about the range of G, so the values that it can achieve, let's look at the domain. So once again, we know the domain is x must be larger than or equal to 5. So first things first, let's plug in x equals 5. That's going to be the lower, or the smallest x value that we can put into our function. So we already know that g of 5, the smallest possible x value, will be equal to 15 over 2 from part A. So then what do we see? Well, we can plug in an infinitely large value for x, into our function g. So what we're going to do, let's try g of, let's put 1,000 in. I know that's not a massive number, but let's just see what happens. If we plug in g of 1,000, so we have 2 times 1,000 plus 5, 2005, over 1,000 minus 3, 997. This gives us 2.011. Okay, so we can actually see when we plug in quite a large number, we actually approach 2. Our fraction becomes closer to 2. We can actually see why this is. If we look at our fraction here, we have 2x plus 5 over x minus 3. But as we put in very, very large numbers into our x's, these 5 and minus 3 don't particularly matter. Because if you plug in a very large number, adding 5 and taking away 3 won't make a very big difference. So we can actually think about it as we plug in a large number, our fraction is approximately 2x over x. And then with that, we can cancel our x's out and we get left with 2. So we can actually see our fraction or our function becomes approximately 2 as we plug in large numbers. However, we can see because we have that plus 5 in the numerator and that minus 3 in the denominator, it's always going to be slightly larger than 2. But the way to think of it is we can say, let's just write it very clearly, as x tends to infinity or a very large number, we can see that g of x tends to 2. Doesn't quite reach 2, it's always going to be slightly larger than 2. So what can we say? We have our range, we have g of x must be less than or equal to, so what did we get when we plug in 5? That's going to be 15 over 2. So less than or equal to 15 over 2, but it has to be larger than, strictly larger than 2, because we know it's never going to reach 2, but it is going to approach 2. So now moving on to part C. What do we have to do for part C? I believe it is, find the inverse function of g, inverse g stating its domain, okay? So first things first, we have inverse of g. So currently our g of x, we have that y equals 2x plus 5 over x minus 3. What do we do when we find the inverse? We swap our x's and our y's. So we swap our x's and our y's, so we can write this as x equals 2y plus 5 over y minus 3. What we're trying to do now, we want to make y the subject of the formula to find the inverse function. Okay, so trying to make y the subject of the formula, we're going to multiply it through by y minus 3. So we get xy minus 3x. So this is just multiplying the left-hand side by y minus 3, or both sides by y minus 3. So we have xy minus 3x equals 2y plus 5, trying to make y the subject. So we want all those y's on one side. So we have xy take away 2y equals 3x plus 5. From here, we're going to factor out our y's. We have we have y times x minus 2 to be equal to 3x plus 5. Then we divide over by x minus 2. So we have that y equals 3x plus 5 over x minus 2. So we have, and that is indeed our inverse function of g. So we have inverse g to be equal to 3x plus 5 over x minus 2. Now, what do they want us to find? They wanted us to find the domain, I believe. So we have to know that of the inverse function, so we have our normal functions, domain and range. If we have the inverse function, the domain becomes the range, and the range becomes the domain. Okay, so what do we know? They want us to find the domain. So this is actually going to be the range of g of x. The domain of the inverse function will be the range of the normal function. So exactly that, we found the range in the previous part, in part B. So that will simply be the domain of our inverse function. So we're going to have that x must be larger than 2 and less than or equal to 15 over 2. That's your final answer to question 1. Alright, so question 2, we have a pretty easy vector question. So we're told relative to a fixed origin O, the point A has a position vector 2i plus 3j minus 4k, and the point B has a position vector 4i minus 2j plus 3k. So straight away, we already know that O to A, I'm going to write these as column vectors just to make it look a little bit nicer, is 2, 3, minus 4. And then we have that O to B, also given the position vector 4b, will be equal to 4 minus 2, that will be 3. So we know that already. And the point C has position vector AI plus 5j minus 2k, where a is a constant and a is less than 0. They're telling us for a reason it's going to be important later on, I would assume. D is a point such that a to b, or the vector a to b, equals the vector b to d. Find the position vector of d. Okay, so first things first, we already know what a to b is. To find the vector a to b, this will simply be o to b, take away o to a. And then we also know that this will be equal to b to d. And we know that b to d will be equal to O to D, take away O to B. Okay, so we already know all this information, which is going to be quite useful. We know these are equal to each other. Once again, A to B, as they gave us in the question, is equal to B to D. So we can say that O to B, sometimes it's easier before even plugging any numbers in, just to write everything out. We have O to B, take away O to A, so this is A to B, will be equal to O to D, take away O to B. So we already know this, so already a lot of information. We can actually add over O to B. Why can we do this? Well, we already know O to B, which we have here. We know O to B again here. We know O to A, which we have here. But the only thing we don't know is O to D. And we're exactly just trying to find the position vector of D. So with all that information, we can actually do a little bit of rearranging. So adding over that O to B, which we have on the right-hand side, we're going to have 2 times O to B. Take away O to A will be equal to exactly what we need, the position vector O to D. So all we have to do now is plug in the numbers. So 2 times O to B, we're going to have 2 times, so O to B will be 4 minus 2, 3. So we have 4 minus 2, 3, and that's going to be take away O to A. O to A is 2, 3 minus 4. So that's going to be 2, 3 minus 4. So what do we have here? 2 times 4 is 8, so we're going to have 8 minus 2. We have 2 times minus 2 is minus 4, so that's going to be minus 4, take away 3, minus 4, take away 3. And then we have 2 times 3 is 6, minus 4, so that's going to be 6 plus 4. So what do we have? We have 8 minus 2 is 6, minus 4 minus 3 is minus 7, and 6 plus 4 is 10. So we have O to D. I would recommend to write it now, back in the form of that I, J, and K. So we have O to D to be equal to 6i minus 7j plus 10k. Okay, perfect. Now moving on to part B. What do we have for part B? We're told that given that the magnitude of A to C equals 4, we have to find the value of A. Okay, so what do we know? We know that A to C will be equal to O to C, take away O to A. Quickly looking back up, we already know O to C and we also know O to A. So O to C, once again, just writing the information down, write down what you know, can help you to find the answer very quickly. O to C is A, 5 minus 2 is a column vector. So we have A, 5 minus 2. And we know from before that O to A will be equal to, looking back up, 2, 3 minus 4. This is 2, 3 minus 4. Okay, so what do we want to find? A to C. A to C is O to C minus O to A. So we actually have A, 5 minus 2, just writing out very clearly so we don't make any silly mistakes. 2, 3 minus 4. Taking one away from the other, we have A minus 2. Then we have 5, take away 3, it's just going to be 2. Then we have minus 2, minus 4. Minus, so it's going to be plus 4. Minus 2 plus 4 is just 2. And then what do we know? We know the magnitude of A to C will be equal to 4. So what does that mean? This means we have to square each component and take the square root to find the magnitude. Just quickly writing that out, we have the square root of A minus 2 squared plus 2 squared, which will be 4, plus 2 squared, which will be 4, and this is equal to 4, the magnitude of the vector AC. Okay, so you could expand the brackets and do the working like that, but that's actually a little bit slower. So what we're going to do is we're going to have, just rewriting this out very clearly, we have A minus 2 all squared plus 4 is equal to, so we're going to square both sides, getting rid of that square root, will be equal to 16. So we have the A minus 2 all squared plus 8 will be equal to 16. We can do 16 take away 8. We get A minus 2 squared equals 8. So from here, what can we do? Take the square root. We have A minus 2 to be equal to, if you're taking the square root of 8, this is actually going to be, plug it in the calculator if you want to check, but it is going to be 2 root 2. But remember, it's plus minus 2 root 2 when taking the square root. So we have that. We're actually run out of space here. I've done a little bit too big. We have the a equals plus minus 2 root 2 plus 2. But then what do we care about? That key bit of information that they gave us before. They told us that a must be less than 0. Highlighting it once again, a must be less than 0. Because a must be less than 0, we're going to have to take the negative 2 root 2. So we're going to have the a equals, let's write it like this, 2 minus 2 root 2. You can plug this into calculator to check. We obviously wouldn't be able to take the positive 2 root 2. That would give us a positive number for a. So we have the a equals 2 minus 2 root 2. And that's your answer for question 2. Okay, question 3, we have a proof statement. We're given the statement, if m and n are irrational numbers where m does not equal m, then m times n, so mn, is also irrational. Disprove this statement by means of a counterexample. Counterexample is actually quite friendly, but first things first, before we start going through the question, let's recap what is an irrational number and what is a rational number. So what is an irrational number? Irrational numbers cannot be expressed as a fraction where the numerator and the denominator are both integers. For example, this could be e, pi, 1 over pi, root 2, root 6. These are all examples of irrational numbers. If we look at rational numbers, these can be expressed as a ratio of integers or a fraction where the numerator and the denominator are integers. So this could be something like 3 over 9, 1.258, 367. These are all rational numbers. Okay, so that's just a little bit of context to the question. So what do we have to do? We have to find two irrational numbers that multiply together to make a rational number, because we're trying to disprove the statement that when we multiply them together, they'll be irrational. So there's actually quite a few things you could take in this question. For example, we could have m equals root 2. We could take n equals 2 root 2, because remember we have to have that m does not equal n. So we have n equals root 2, n equals 2 root 2. We can quickly say these are both irrational. So we have two irrational numbers. These are both irrational. And then if we do m multiplied by n, so we have root 2 multiplied by 2 root 2, this will be equal to 4, which is rational. 4 is a rational number, so we say which is rational. Therefore, so we have two rational numbers which were not equal, we multiplied them together and it gave us a rational number. So we have which disproves the statement, which disproves the statement. That's all you have to say. Be very careful, but make sure you have to say that summary statement. So therefore, disproving the statement, right? Because we said they were both irrational. We made a rational number, disproving the statement. You could write a little bit more if you want to be careful, but this is the key thing, making that summary statement. You could use other numbers like root 20 multiplied by root 5, for example. That'll give you root 100, which is then 10. You could do pi multiplied by 1 over pi. That's just going to be 1. These are all other examples that you could use and would be fine. Okay, so on to BI, we have to sketch the graph of y equals the modulus of x plus 3. So what we're sketching y equals the modulus of x plus 3. Let's take this step by step. First things first, let's just draw out the modulus of x graph. That's just y, that should be straight, y equals the modulus of x. So what do we know? We're adding 3 to this. Adding 3 means we're adding 3 to every single y value. In other words, we're shifting that whole graph up by 3. Okay, so shifting that whole graph up by 3, we draw that V-shaped modulus of x graph, but in this case, our y-intercept will be at 3. So that's simply sketching out the graph of y equals the modulus of x plus 3. Now, let's look to part BII. We have to explain why the modulus of x plus 3 is larger than or equal to the modulus of x plus 3 for all real values of x. So let's just quickly write that out. We're trying to show modulus of x plus 3 is larger than or equal to the modulus of x plus 3 for all real values of x. Now, because we've already sketched the graph out of y equals the modulus of x plus 3, the most obvious way to do this question would be to simply then sketch out the graph of the modulus of x plus 3, so the right-hand side here. And then we can compare and see if this inequality does indeed hold. So when sketching out this graph, the first thing that I'm thinking, let's just draw out the line. You could already know that this is just the modulus of x graph shifted 3 to the left. But the first thing I'm thinking is just to draw out the line of x plus 3, and then we can apply that modulus function onto it. So drawing out the line of x plus 3, this will simply be straight line with that y-intercept at 3, and then going down. But because this is a modulus function, we know that it cannot achieve negative y values. Therefore, we will have to reflect in the x-axis like this. We know it's going to be parallel to the modulus of x plus 3. So we reflect it in the x-axis. So now we have our line, we have our line of y equals the modulus of x plus 3. So now that we've sketched them all out, we can look at our inequality. So what are we trying to show? We're trying to show the modulus of x plus 3 is larger than or equal to the modulus of x plus 3. We can see this is actually the case, because if we look, we can quickly see, or we can say, by looking at sketch, So by looking at a sketch, just looking at the graph, we can see that for x, 4x larger than or equal to 0, 4x larger than or equal to 0, we can see that these graphs are actually equal, right? Because the lines continuous with the same gradient going through each other, going through that y-intercept of 3. So for x larger than or equal to 0, we have that the modulus of x plus 3 equals the modulus of x plus 3. Okay, so far the inequality is holding, and then we can say for all these negative x values, looking at the left-hand side here, we can indeed see that the modulus of x plus 3, this dark blue line here, is indeed above our red graph of y equals the modulus of x plus 3. So we can say for x less than 0, we have that the modulus of x plus 3 is larger than the modulus of x plus 3, just by looking at the graph. Therefore, so what do we have to say? Explain why the modulus of x plus 3 is larger than or equal to the modulus of x plus 3 for all real values of x. So that we can say, just to kind of finish off the proof, we can say, therefore, the modulus of x plus 3 is larger than or equal to the modulus of x plus 3 for all, just summarizing here, for all real values of x. Okay, so that's all you have to say for part BII. Now moving on to question 4. So question 4, we actually have quite a tricky series question. For part I, we have to show that the summation, so don't get intimidated by the summation notation. It's just a summation from r equals 1 to r equals 16. So we plug in r equals 1, 2, 3, all the way up to 16 of 3 plus 5r plus 2 to the power of r equals 131,798. Now here's the thing, here's a little tricky thing to know for these questions. Because we're just adding every term together, we can actually split up our summation notation. We can actually rewrite this as, look for the individual term from r equals 1 to 16 of 3. Look at the summation from r equals 1 to 16 of 5r. And then look at the summation from r equals 1 to 16 of, I believe it was 2 to the power of r. 2 to the power of r, perfect. So, once again, if in doubt with summation notation, write out a few terms. Always good to write out a few terms, especially in this question. So, because we have a summation from r equals 1 to 16 of 3, this will simply be 3 plus 3 plus 3, and so on 16 times. So this will actually be equal to 16 times 3. So just looking at this summation from r equals 1 to 16 of 3, 16 times 3 is going to be 48. Remember, we're going to add all of these together at the end, but for now, look at them individually. So, same thing with the 5r. Plug in r equals 1, this will give us 5. Plug in r equals 2, we get 10, plus 15 for 3, and so on, just plugging all the way to 16. So here we have to actually spot this is an arithmetic series. Arithmetic series, we know that the formula for this will be n over 2 multiplied by 3 plus n minus 1d, where we have n minus 1, so n is the number of terms, d is the common difference, and a is the first term. Okay? So what do we have here? We have the first term, it's going to be 5. We have the common difference, well, what's happening each time? We are adding 5 each time, so the common difference is going to be 5. And then we have the number of terms, where we can quickly see that this is from r equals 1 to r equals 16, so we're going to have 16 terms. So let's just plug this into the formula. So we have n over 2, 16 over 2, multiplied by 2a, so that's 2 times 5, it's going to be 10. Then we're going to be adding on n minus 1, so that's 16 minus 1, so that's going to be 15 multiplied by the common difference, which is 5. So let's just put this into our calculator very quickly. So we have, looking inside the bracket first, so we have 15 times 5, answer plus 10, answer times 8. So this is going to give us 680, looking at the summation from r equals 1 to 16 of 5r. Now focusing on 2 to the power of r. So remember, this was in an arithmetic series. Quickly labeling that just to make things very, very clear. Arithmetic series, or arithmetic series, however you want to say it. Now we have 2 to the r. Same idea. Plug in r equals 1, gives us 2. Plug in r equals 2, this gives us 2 squared, which is 4. Plugging in 3 gives us 8, and so on. So what do we see here? Well, this is actually a geometric series. Why is it a geometric series? Well, we have a common ratio each time we're multiplying by 2, because we're increasing that power up by 1 each time. So 2 to the power of 1, 2 to the power of 2, so on. So what is our geometric series formula? Geometric series. Quickly writing it out. So the geometric series, because of that common ratio, and the formula would be a multiplied by 1 minus r to the n over 1 minus r. Remember, r is a common ratio, which we see to be 2. We have that r equals 2. We have a, the first term, is 2, because we wrote them out. First term was 2. And we have n, the number of terms, to be, we're going from r equals 1 to 16, sorry. So we have that n equals 16. So just plugging it into the formula, we have 2 multiplied by 1 minus 2 to the power of 16. I believe n is, yep, r is 2, perfect. All over 1, take away, our common ratio is 2, so that's 1 minus 2. Plug this into your calculator, doing 2 to the power of 16, 1 minus our answer multiplied by 2, then answer divided by 1 take away 2, so that's going to be minus 1. This gets us an answer of 100,000, oh sorry, 131,070, so 131,070. So what do we have to do now? Last step, remember we were summating all of these terms in our original expression, so we just have to add everything together. So we do, looking at each thing individually, we have this 48 here, we have this 680 here, and we have this 131,070. So just adding them together, put it in the calculator, we have 48 plus 680 plus 131,070 will be equal to, quickly put it in the calculator, plus 680, we get 131,798. Is that what they wanted? That is indeed what they wanted, so that is your answer to part I. So moving on to II, we're told a sequence u1, u2, u3 is defined by un plus 1 equals 1 over un. So the next term will be 1 over the previous term. u1 equals 2 over 3, so 2/3. Find the exact value of the summation from r equals 1 to 100 of ur. So u1, u2, u3, all the way up to u100. We're summating all these together. Okay, perfect. So in these kind of questions, there tends to be a pattern that you have to recognize. It could be using log rules or something like that. In this case, let's try write out a few terms. So what do we have? We have the first term to be 2/3. Let's try find the second, third, and fourth term, just to make things a little bit easier. So we have that u1 equals 2 over 3. We know that u2, so u2 will be 1 over the previous term, so that's going to be 1 over 2/3. 1 over 2/3 equals 3 over 2. Okay, so we actually have that u2 will be equal to 3 over 2. Now looking at u3, focusing on u3 here, u3 will be equal to 1 over u2, and u2 is 3 over 2. So 1 over 3 over 2, I think we're seeing a pattern here. We have that u3 will be equal to 2/3. And we can actually see that this pattern will keep on repeating and repeating and repeating. So we have 2/3, therefore u4 will be 1 over u3, which will be 3 over 2. So we can actually see for all of our odd u's, so u1, u3, u5, we're going to get 2/3, and then for all of our even u's, so second term, fourth term, sixth term, we're going to get 3 over 2. So we can actually see that our summation from r equals 1 to 100 of ur will actually be equal to, so let's think about it. If we're going all the way to 100, that means we're going to have 50 times 2/3 for all the odd numbers, and then 50 times 3 over 2 for all of the even terms, right? So that's exactly it. We have 50 multiplied by 2/3, and then we're going to be adding on to that 50 times 3 over 2. Okay. So just slap this into your calculator. We get 50 times 2/3, 50 times 2/3, then onto that we add on 50 multiplied by 3 over 2. That gives you a final answer of 325 over 3. So it's actually quite an easy question in the end. The key thing with these kind of questions, write out a few terms, spot a pattern, and see how that relates to the question. But that's it. On to question 5. Okay, so on to question 5, we have a Newton-Raphson question. We're told the equation 2x cubed plus x squared minus 1 equals 0 has exactly one root. For part A, we have to show, for this equation, the Newton-Raphson formula can be written as xn plus 1 equals 4xn cubed plus xn squared plus 1 over 6xn squared plus 2 times xn. Okay, so quickly reminding ourselves of the Newton-Raphson formula, we have that xn plus 1 equals xn, take away our function, plugging in xn, so f of xn, over the derivative of our function, so f dash of xn. So perfect. So what is our function? Our function, the equation we're using, is this 2x cubed plus x squared minus 1 equals 0. So our function of xn will be equal to, quickly reminding myself, 2x cubed plus x squared. So we're going to have 2 times xn cubed plus, then we have xn squared minus 1. We have xn squared minus 1. Okay, so we then have the derivative. So finding, f dash of xn, differentiating. Bring that power down to the front, take 1 off the power, 2 times 3, so we're going to have 6 times xn squared plus 2 times xn, and that constant will disappear. So what we have to do now is plug everything into the formula, and then we're going to rearrange and simplify just to get it into the form they want for part A. So plugging everything in, we have that xn plus 1, just using that Newton-Raphson formula, is equal to xn take away. So f of xn is going to be 2xn cubed plus xn squared minus 1 That's going to be all over f dash of xn. So it's going to be over 6xn squared plus 2 times xn. So let's see what they want. Well, their answer they have for part A, we have everything as one fraction, right? So we're actually going to have to just use a little bit of, well, we're just adding the fraction. So we're going to have to multiply this xn, top and bottom, by 6xn squared plus 2 times xn to get the same denominator, so then we can add the fractions, or in this case, take them away. So what do we have? We are going to have xn multiplied by 6xn squared plus 2xn. Then we're going to be taking away from that, or writing everything in brackets to make sure we don't make any silly mistakes, taking away 2xn cubed, so it started raining, I don't know if you guys can hear, plus xn squared minus 1. Okay, so from here, this is all going to be over, because we've got the same denominator, so this is all going to be over 6xn squared plus 2 times xn. Okay, so let's sort out that numerator. Quickly sorting out the numerator, we have 6xn squared times by xn, so that's 6xn cubed plus 2xn squared. Then we're going to be taking away 2xn cubed. Be careful with your signs here. So it's going to be minus xn squared and then plus 1. So minus minus, we're going to have plus 1. And once again, that's all going to be over 6xn squared plus 2 times xn. So let's sort out that numerator a little bit better now. So we have 6xn cubed minus 2xn cubed. So that's going to be 4xn cubed. Looking at our x squareds, we have 2xn squared minus xn squared. So that's going to be just plus 1xn squared. And we're going to have plus 1. That's all going to be over 6xn squared plus 2 times xn. And remember, this will be equal to xn plus 1, because it's the Newton-Raphson formula. And quickly comparing it, is that what we need? That is exactly what we need. 4xn cubed plus xn squared plus 1 over 6xn squared plus 2 times xn. So we've shown that just using the formula. That is your answer to part A. Okay, so moving on to part B of this question. Part B of this question, what do they want? They want, using the formula given in part A with x1 equals 1, find the values of x2 and x3. This is very easy, a little bit of calculator work. So x1 equals 1, so we set 1 equal to the answer. Then whenever we have xn, we plug in our answer in. So we plug in our answer, put it in your calculator. So we have x1 equals 1, and then what we would do, we would have 4 times 1 cubed plus 1 squared plus 1 over 6 times 1 squared plus 2 times 1, so plus 2. Right, we can actually do this in our head here. We have 4 plus 1 plus 1 is going to be 6. In the denominator, we have 6 plus 2, which is going to be 8. So this would be 6 over 8, which does equal 3 quarters for x2. So we have that x2 equals 3 quarters, but I would recommend just setting 1 equal to the answer, then putting it into your calculator. Then to get x3, all you have to do is plug in 3 quarters, or already have it as the answer in this equation. Set equals, again, after your x2, we get x3 to be equal to 2/3. Just some iteration work. Nothing too bad there. Moving on to part C. Part C, what do they want? Explain why, for this question, the Newton-Raphson method cannot be used with x1 equals 0. So the key thing is, when using the Newton-Raphson method, f dash of xn cannot be equal to 0. Okay, so let's check that. If we have f dash of 0, we have, going back to f dash of xn, which we had to be 6xn squared plus 2xn. So quickly writing that up here, we had f dash of xn to be equal to 6xn squared plus 2 times xn. We can see f dash of 0, this will be 6 times 0 squared plus 2 times 0. So that's going to be equal to 0 plus 0, which equals 0. Okay, so f dash of 0 does indeed equal 0. So we can say at x1 equals 0, f dash of 0 is a stationary point. We can just say we have a stationary point at x1 equals 0. Is a stationary point. And we can also say in the formula, so what does that mean? We would be dividing by 0. We divide by 0, which we know is undefined. So we cannot have x1 equals 0, because we'd have that f dash of xn, or f dash of 0, is equal to 0, so it would not work for the Newton-Raphson formula. On to question 6. Okay, question 6, here we go. We're told that f of x equals minus 3x cubed plus 8x squared minus 9x plus 10. We have to calculate f of 2. So it's quite friendly. All we have to do is plug in 2. There we go, plug in 2 into our function. It's quite friendly. So what do we have? We have minus 3. We're going to write out the working here just to be safe. Minus 3 multiplied by 2 cubed plus 8 times 2 squared That's going to be minus 9 times 2. That's going to be plus 10. So you could do this in the calculator. I'm doing it in my head here. I think it's not too bad. So 2 cubed is 8. Minus 3 times 8. That's going to be minus 24. Plus 2 squared is 4. 8 times 4 is 32. Take away 18 plus 10. So what do we have here? So we have 32 plus 10. So it's going to be 42. Take away minus 24 minus 18 is also going to be, so it's minus 42. So we have 42 minus 42. That's going to be equal to 0. So moving on to part II, what do we have to do? We have to write f of x as a product of two algebraic factors. So we've just seen f of 2 is equal to 0. What does that mean? This means that x minus 2 is a factor. So we know that x minus 2 is a factor. So they want us to write it as a product of two algebraic factors. So what we're going to do is we're going to divide our minus 3x cubed. So what do we have? We have minus 3x cubed plus 8x squared minus 9x plus 8x squared minus 9x, and I believe it was plus 10. We're going to have to divide that by x minus 2, okay? So a bit of polynomial algebraic long division. Let's go. So how many x's go into minus 3x cubed? That would be minus 3x squared, and we multiply down. So minus 3x squared multiplied by x, we get that minus 3x cubed. And then we're going to be doing minus 3x squared multiplied by minus 2, so that's going to be plus 6x squared. Now what do we do here? We take away one from the other. So we have these minus 3x cubed cancel out, as we know. Then we have 8x squared, take away 6x squared. That is going to be 2x squared. We rewrite that 9x. And then, so how many x's go into 2x squared? This will just be 2x. So we're going to be adding on 2x. Then multiplying down, we have 2x times by x is 2x squared. Then doing 2x multiplied by minus 2, this is going to be minus 4x. Same thing as before. Take one away from the other. Minus 9x minus 4x, so that's plus 4x. We are going to get minus 5x, and we have that plus 10. So how many x's go into minus 5? Oh, sorry, how many x's go into minus 5x? That would be minus 5. Multiply down through, we have minus 5x. Minus 5 times minus 2 is plus 10. So once again, taking one away from the other, minus 5x minus minus 5x, those cancel of course, and then 10, take away 10 is equal to 0, so no remainder. So we actually have x minus 2 multiplied by minus 3x squared plus 2x minus 5. And that is exactly what they wanted. They wanted exactly that. Write f of x as a product of two algebraic factors. We have that f of x equals x minus 2 multiplied by minus 3x squared plus 2x minus 5. Okay, so for part A, we had that f of x equals x minus 2 multiplied by minus 3x squared plus 2x minus 5. Moving on to part B. What do we have for part B? So using the answer to AII, that's very important information, we have to prove there are exactly two real solutions to the equation, minus 3y to the 6 plus 8 times y to the 4 minus 9y squared plus 10 equals 0. Now we have to be able to see this looks very, very, very similar to what we had in part A. They want us to use the answer to part A eventually as well. So whenever we have these kind of questions, try compare it to what you had earlier in the question and see what you have to do. Now we can see actually, if we make the substitution that x equals y squared, we actually have what we have in part B with these y's will be exactly equal to what we had in part A. Let's start with f of x. So let's just write out what we currently have with y squared. So we have minus 3y to the 6, and what do we have? We have plus 8y to the 4 minus 9y squared. So that's plus 8y to the 4 minus 9y squared. And I believe it was plus 10, okay? So that's plus 10. Now we're going to make the substitution of x equals y squared. The easiest way to spot this is we can see we have minus 9x, and that goes to minus 9y squared. So making that substitution of y squared equals x seems to be appropriate to make it look like what we already used and know in part A. So we're going to use that x equals y squared. So rewriting this, we have minus 3x cubed plus 8x squared minus 9x plus 10 equals 0. So this is exactly what we have using that substitution, what we had in part A. Now what do we know? We know we can actually factor these out because we actually have to write it as a product of two algebraic fractions, right? So factors, sorry. So we simply know that this is already, this will be equal to x minus 2 multiplied by minus 3x squared plus 2x minus 5. So we're trying to find the solutions. What they want us to find, they want us to show that there are exactly two real solutions. So we know one solution, thinking in x for now, we'll convert it back to y later on. So thinking in x, we have one solution. Remember, this is all equal to 0. So one solution will be x equals 2. And the second solution, you can actually put this into your calculator and you'll see that we get no real solutions. but we want to just make sure and show that there are no real solutions. So to do this, we will show that our discriminant b squared minus 4ac will be less than 0. So showing this now, we have b is 2, so we're going to have b squared is 4. Take away 4 times a, so that's minus 4 multiplied by minus 3 multiplied by minus 5. This will give us 4, take away 4 times minus 3 times minus 5. Minus 3 times minus 5 is 15. 4 times 15 is 60, so that's take away 60, which equals minus 56, which is indeed less than 0. Therefore, no real solutions. Okay? So we can ignore this factor of minus 3x squared plus 2x minus 5. So we're just going to focus on that x equals 2. But remember, we use the substitution that x equals y squared. We use x equals y squared, so we have y squared equals 2. Therefore, y will be equal to plus minus root 2. And those will be the two solutions. We have y can be root 2, or we have y equals minus root 2. And that is your answer to part B. Okay, so for part B, we can say therefore we have two real solutions as y can be root 2 or y equals minus root 2, and the quadratic had no real solutions. Now moving on to part C. What do we have for part C? We have to deduce the number of real solutions for theta larger than or equal to 7 pi less than 10 pi to the equation 3 tan cubed theta minus 8 tan squared theta plus 9 tan theta minus 10 equals 0. So comparing this back to part A, we can see this is almost the same, but instead of x, we have tan theta, and we can see the whole thing is multiplied by minus 1. But because this is equal to 0, we can multiply both sides by minus 1, and it wouldn't change the solutions. Okay, so that's completely fine. So this is actually just f of tan theta. So we can work from there. Because we know this is f of tan theta, so once again, this is f of tan theta. And what do we know about the solutions? We're using that algebraic factorization. We had that x minus 2, and we had that minus 3x squared plus 2x minus 5. But we know all of this had no real solutions, so we don't care about it. So we have the x minus 2. But instead of x, we have tan theta here. So what do we care about? We care about the solution of tan, let's write it up here actually. We care about the solution of tan theta equals 2. Because remember, this is f of tan theta equals 0. We have tan theta minus 2 as a solution, so tan theta will be equal to 2. Now here's the thing, theta must be larger than or equal to 7 pi and less than 10 pi. So I'm going to explain this. You could quickly know that we are going to get a solution every single pi. So we'd have 3 solutions. But just to make this super clear, if we draw a tan theta graph out, just from, for example, 0 to pi, this is 0 to pi, we can see at tan theta equals 2, I'm going to label that axis, this is theta, this is y, tan theta equals 2, we get one solution up to pi. If we were to continue drawing it out up to 2 pi, we would once again get another solution. Then drawing it all the way to 3 pi, once again we'd get one more solution. So all of these, not the neatest, but all of these, quickly highlighting it, would be our solutions. Get one solution here, one solution here, and one solution here to 3 pi. It's the same idea. From 7 pi to 10 pi, this is a difference of 3 pi. Therefore, we can quickly say, therefore, for theta larger than or equal to 7 pi, less than 10 pi, and tan theta equals 2, we get 3 solutions. 3 solutions. That's exactly it. That's all you have to say, and that's your answer to part C. Because we have shown, we've deduced the number of real solutions to be 3. On to question 7. Okay, so question 7, we have to solve for x larger than or equal to 0, less than pi over 2, the equation 4 sine x equals sec x. So we have 4 sine x equals sec x. We can rewrite sec x as 1 over cos x. So we have 4 sine x equals 1 over cos x. Only logical thing to do is multiply over by cos x. So we have 4 sine x cos x equals 1. Now what do we have to spot? We have to spot the sine double angle ID. Sine 2x we know to be 2 sine x cos x. We have 2 sine x cos x. We have 4 sine x cos x. So multiplying both sides by 2, we have 2 sine 2x to be equal to 4 sine x cos x. So from here we can make this substitution. So we have 2 sine 2x equal to 1. Divided over by 2, we have sine 2x to be equal to a half. Take the inverse sine of a half. So we have 2x be equal to the inverse sine of a half. Key thing to remember, guys, look at the question. We are in between 0 and pi over 2, therefore we must be in radians, okay? So taking the inverse sine of a half, that gives us pi over 6. Taking the inverse sine of a half, we have pi over 6. So we have that 2x pi over 6. Remember, let's think about the range. So right now we know that x must be larger than or equal to 0 and less than pi over 2. We're currently solving for 2x. So when solving for 2x, we have that 2x must be less than pi and larger than or equal to 0, multiplying both sides by 2. Therefore, the secondary value, we know when solving for sine, we do pi, in radians at least, we do pi minus our primary value. Primary value was pi over 6. Secondary value will be 5 pi over 6. Anything else by adding 2 pi to get further solutions would be outside of our desired range. So we don't worry about that, but we're just trying to solve for x. So we have that x equals dividing over by 2, x equals pi over 12, and x equals 5 pi over 12. Now moving on to part II, I believe. So what do we have to do for part II? So there's pi over 12 and 5 pi over 12 for part I. So we have to solve for theta larger than or equal to 0, less than 360. So immediately I'm going into degrees because we're in degrees now. The equation 5 sine theta minus 5 cos theta equals 2. A few different ways to do this. I'd say the most efficient way is to rewrite this as r sine theta minus alpha. We use minus with our sine addition formula because we have sine theta minus cos theta. Just going to make it a little bit easier. So let's solve this quickly. So what do we have? We have 5 sine theta, take away 5 cos theta, okay, and we're going to write it in the form of r sine theta minus alpha. Great. So we know to find r with these trig modeling techniques. All we have to do is find the square root of 5 squared, so looking at our 5s here, 5 squared plus 5 squared, so this will be equal to r. So we have that r equals the square root of 25 plus 25 equals root 50. Root 50 can be rewritten as 5 root 2. So we know r equals 5 root 2. Then what we're going to do, we're going to expand out this r sine theta minus alpha using our sine addition formula. So what do we have? We have r, actually let's keep it r outside. For the start, we have r sine theta cos alpha, take away cos theta sine alpha. Expand out the r, we have r sine theta cos alpha, take away r cos theta sine alpha. Now we're going to compare this to what we originally had. We had 5 sine theta and 5 cos theta. Now because we have 5 sine theta, this means that r cos alpha must be equal to 5. And we have that r sine alpha must also be equal to 5 because we had minus 5 cos theta. Okay, so from here to find alpha, we can divide one equation by the other. Dividing r sine theta equals 5 by r sine alpha equals 5 by r cos alpha equals 5. We're going to be left with the r's will cancel. We get sine divided by cos, which will be tan alpha. 5 divided by 5 is 1. Remember, we are in degrees for this question, so this will give us alpha equals the inverse tan of 1. Alpha equals 45 degrees. So there we have it. We have 5 root 2 as our r value, sine theta minus 45. From here, we can now solve the equation. So what are we trying to solve? We're trying to solve 5 sine theta minus 5 cos theta equals 2. So remember, 5 sine theta minus 5 cos theta is equal to 5 root 2 sine theta minus 45. So we have 5 root 2 sine theta minus 45 will be equal to 2. First things first, let's divide over by 5 root 2. So we have that sine theta minus 45 will be equal to 2 over 5 root 2. Now remember, what is our restriction of theta? Theta must be larger than or equal to 0, less than 360. So what we're going to do, we have theta minus 45 to be equal to the inverse of sine of 2 over 5 root 2. But remember, so now we're solving for theta minus 45. So if we're solving for theta minus 45, what's the range of values we can accept? Well, we're going to have to take away 45 from both sides. So we have minus 45, and then we also have 360 minus 45 is 350. So solving here, remember we are in degrees, the calculator must be in degrees now. Take the inverse sine of 2 over 5 root 2. So we get a primary value for theta minus 45. Theta minus 45. Key thing again, guys, look back at the question, look at what they tell us. They tell us that our answers are to 1 decimal place, very important. So that primary value is going to be, take the inverse sine of 2 over 5 root 2, 16.4, so we get 16.4. Secondary value, we're going to do 180 minus the primary value, so 180 minus 16.4 is going to be 163.6. We get 163.6. Now we can actually see from here, if we started adding 360 or taking 360 to either of our solutions, it would be outside of our acceptable range, so we don't have to worry about any of the solutions. But we don't care about theta minus 45, we care about just theta. So to find our solutions for theta, we're going to have to add 45 to both solutions. 16.4 plus 45, that gets us 61.4. So we have 61.4 as our first solution. Our second solution would be 163.6 plus 45, that gets us 208.6. So our two solutions for theta within our range of theta larger than or equal to 0, less than 360, will be 61.4 and 208.6. That's your final answer to question 7. Okay, so question 8, we're told figure 1 is a graph showing the trajectory of a rugby ball. The height of the ball above the ground, h meters, has been plotted against the horizontal distance, x meters, measured from the point where the ball was kicked. Okay, the ball travels in a vertical plane, and the ball reaches a maximum height of 12 meters and hits the ground at a point 40 meters from where it was kicked. Okay, find a quadratic equation linking h with x that models the situation. So first things first, before we even start using the information that they've given us, we have h quadratic equation linking h with x. So we want to form a quadratic equation. In general, this will take the form of h equals ax squared plus bx plus c. Now let's think about the information they give us. What did they tell us? So first of all, we know our origin is going to be 0, 0. So we're going to be 0, the ball will be 0 height above the ground, 0 meters above the ground, and we haven't traveled horizontally yet because we haven't kicked the ball yet. We also know that we're going to hit the ground 40 meters from where it was kicked. So our h will be equal to 0 when x equals 40 as well. So this end point here will have coordinates 40, 0. And we also know that we reach a maximum height of 12 meters. And because it's a negative quadratic, so this maximum point will be 12 meters, h will be 12. Because it's a negative quadratic, it's going to be symmetric. So our x value will be halfway in between 0 and 40, which will be 20. So we actually have the coordinate of 20, 12. From here, we can start plugging in all of these three coordinates into our quadratic equation. So let's start with 0, 0. So when h equals 0, x equals 0. So we have that 0 equals a times 0 squared, which is 0, plus b times 0, which is 0, plus c. So we have that c equals 0. So we can already get rid of that c from that quadratic equation. So what else do we know? Let's plug in 40, 0. So when x equals 40, h equals 0. So we have 0 equals a times 40 squared plus 40b. And then we can ignore the c because we know it equals 0. So we have that 0 equals 40 squared is 1,600. So that's 1,600a plus 40b. Now let's plug in our third coordinate of 20, 12. So when the height is equal to 12, we have x equal to 20. So we have a times 20 squared, it's going to be 400, plus 20b. So now let's write out our simultaneous equations. So we have that 1,600a plus 40b equals 0. And then we also have 400, so that's 20, 400a plus 20b to be equal to 12. So this is just GCSE simultaneous equations. Let's multiply our bottom equation by 4. Why not? So we have 1,000, writing out both equations once again, 1,600a plus 40b equals 0. And then we have multiply our bottom equation by 4. 1,600a plus 80b equals 48. Now let's label this equation 2, label this equation 1. Let's do equation 2, take away equation 1. So 1,600a is cancelled out. We have 80b minus 40b, so we have 40b equals 48 minus 0. It's just going to be 48. So we have b equals 48 divided by 40. So we have b equals, that would be 12 over 10, which equals 1.2. So b is equal to 1.2. Now to find a, just sub this back into either equation. So we know that 1,600a will be equal to minus 40b, because plus 40b is equal to 0. So we have 1,600a equals minus 40b. Sub in b equals 1.2. So we have that a equals minus 40 multiplied by 1.2 over 1,600. Plug that into your calculator. So minus 40 times 1.2, minus 40 times 1.2, give me a second, sorry guys, divided by 1,600 is minus 0.03. That's minus 0.03. So a to be minus 0.03 and b to be 1.2. So our quadratic equation will be h equals minus 0.03x squared plus 1.2x. Great. So now moving on to part B. What do we have to do? The ball passes over a horizontal bar of a set of rugby posts that is perpendicular to the path of the ball. The bar is 3 meters above the ground. Use your equation, so quadratic equation that we found, to find the greatest horizontal distance of the bar from our origin, so from where we kick the ball. Okay, so our height, once again, our height is 3 meters. H equals 3 meters at these rugby posts. So we want to find the greatest value of x when h equals 3. So sub in h equals 3, we have 3 equals minus 0.03x squared plus 1.2x. I know your immediate instinct, which is the correct instinct, is to take away 3 to set the whole equation equal to 0. So we have minus 0.03x squared plus 1.2x, take away 3 is equal to 0. Slap that into your calculator to solve the quadratic. So we have, solving the quadratic, minus 0.03, we have 1.2, and then we have minus 3. So that gives us two solutions to x. We get x can be equal to 20 plus 10 root 3 or 20 minus 10 root 3. So we get x is equal to 20 plus minus 10 root 3. However, we want the greatest horizontal distance, right? So 20 plus minus, so h equals 3 meters, right? H equals 3 meters. Looking at our quadratic, there could be two solutions. We're going to have one solution over here, and we have another solution going all the way across to this larger value of x. We care about the larger value of x. Why do we care about this? Because that's what they want in the question. They want the greatest horizontal distance. So which one will be greater? Is it 20 plus 10 root 3? 20 minus 10 root 3 is going to be 20 plus 10 root 3. So we care about x equals 20 plus 10 root 3. If you want to get this as an actual answer and not leaving it as 20 plus 10 root 3, this would give us 37.32 to 2 decimal places. So we have 37.32 meters. That's the 2 decimal places. Okay, that is perfect. Remember, make sure to use the correct units. We do have meters. Okay, part C, give one limitation of the model. So there's quite a few things you can say here. Quite a few things. I mean, we're saying the ball travels in a vertical plane. There's many things which we haven't considered. So if you refer to the model when answering this question, I'm going to write down 2 or 3 things that you could say. So 2 things you could immediately say is the model ignores wind, any potential wind blowing that rugby ball around. You could also say it ignores air resistance. What else does it ignore? We could say the model doesn't account for what doesn't account for. When you kick a rugby ball, is it perfectly still as it's going? No, the ball spins. So we could say it doesn't account for spin of the ball. So these are just some things that you could say. Any one of these things would get you the mark. Doesn't account for spin of ball. So each of these things would be okay. 1, 2, or 3 all would get you the marks that you need for this question. And that is question 8. On to question 9. Okay, question 9, differentiation from first principles. Given that theta is measured in radians, prove from first principles that d theta of cos theta equals minus sine theta. You may assume the formula for cos A plus minus B, and that as h tends to 0, sine h over h tends to 1, and cos h minus 1 over h tends to 0. So quickly recalling the formula for differentiation from first principles, we have that f dash x equals the limit as h tends to 0 of f of x plus h minus f of x all over h. Okay. So remember, we're not going to be working with a function of x here. It's going to be theta. So we have our function of theta will be equal to cos theta. Okay. So we have the f dash theta will be equal to the limit as h tends to 0. So lim h tends to 0 of. So instead of plugging in theta, we're going to plug in theta plus h. So remember, it's not a whole function plus h. We're plugging in x plus h, in this case, theta plus h, into our function. So we have cos of theta plus h. Take away cos of theta. That's going to be all over h. Okay, so here we're going to use the cos addition formula. So we have, actually I'm not going to write it out every time, what we are going to write out every time just to be safe is the limit as h tends to 0 of cos theta cos h. Take away sine theta sine h. That's just the cos addition formula. Take away cos theta. That's going to be all over h. Now here we're going to have to use what we were given in the question. So we were given 2 key bits of information in the question, that as h tends to 0, sine h over h tends to 1, and cos h minus 1 over h tends to 0. So those are the 2 key bits of information that we're going to have to use. First, we have to create these pieces of information essentially by doing a little bit of rearranging. So we want that cos h minus 1. We can see we can actually factor out cos theta from here. So what we left with a limit as h tends to 0 of, so factoring out like cos theta, we get cos h minus 1 all over h. It's a horrible line. All over h. There we go. That's going to be take away sine h over h sine theta. Okay, perfect. So now we can actually take the limit. So we take the limit as h tends to 0. So cos h minus 1 over h tends to 0, and sine h over h tends to 1. We can actually write that out. We can say as h tends to 0, cos h minus 1 over h tends to 0, and sine h over h tends to 1. Perfect. Okay. So we take that limit. So what we're left with cos theta multiplied by 0, take away sine theta multiplied by 1. Okay, so what we're left with, well, cos theta times 0 is just 0, so we're left with minus sine theta. And that will be equal to f dash theta, which is exactly d theta of cos theta. And that's your answer. Nothing too tricky, a little bit of differentiation from first principles, just applying the formula and using the information they give you in this question. Okay, so on to question 10. We have a spherical mint of radius 5 millimeters is placed in the mouth and sucked. 4 minutes later, the radius of the mint is at 3 millimeters. In a simple model, the rate of decrease of the radius of the mint is inversely proportional to the square of the radius. Using this model and all the information given, find an equation linking the radius of the mint and the time. So first of all, we have some information. We're told that the radius is 5 at the start, so when the time is 0. 4 minutes later, the radius of the mint is 3 millimeters. So let's just define our variables. As they say, you define the variables that you use. So let's just say the time equals, in minutes, so let's say time sucked, or time sucking mint, okay? Time sucking mint. This is going to be in minutes. Why is it in minutes? Because they give us the information in minutes. I'm going to say R equals radius of mint, and they give it to us in millimeters. So we're going to say radius of mint in millimeters. Okay, so from here, let's use the information they give us. So we say the radius is 5 at the start, so r equals 5 when t equals 0, and then when t equals 4, so 4 minutes later, we have the r equals 3. This will be useful later on. We have a feeling it's going to be a differential equation when we get given information, because we're going to have to use that to find the constant of integration normally. But let's just see where we go. So from here, moving on, we have the rate of decrease of the radius of the mint is inversely proportional to the square of the radius. So whenever I see rate of decrease, you have to be thinking time. So rate of decrease of the radius of the mint inversely proportional to the square of the radius. Remember, inversely proportional means we're going to have something over, in this case, the square of the radius. So it's going to be something over r squared. So what do we have? The rate of decrease of the radius of the mint. So that's going to be dr dt, changing the radius, changing time. So thinking about the time now, rate of decrease will be proportional to minus. Why is it minus? Because it's a decrease, with decrease in the size of the radius, so minus 1 over r squared. That fish sign just means proportional to. We can write this as dr dt equals minus k, where k is a constant, over r squared. So we can actually just quickly say k is a constant. Okay, so from here, what can we do? It's going to be a differential equation. So solving the differential equation, we have to get all of our r's on one side and all of our t's on the other. So we're going to multiply over by r squared. So we have r squared dr to be equal to minus k dt. All we have to do now, integrate both sides. So integrating r squared, raise that power up by 1, divide by the new power. So that's going to be a third r cubed to be equal to minus kt plus c. So there's two unknowns. We have k and we have c unknown. So we're going to have to use two pieces of information. First of all, we know when the time is 0, we have that the radius is equal to 5. So let's plug that in. So we have a third multiplied by 5 cubed. That's going to be 125 over 3 equals minus k times 0. That's all just 0. So that's going to be equal to c. So we have that c equals 125 over 3. And we're going to use that answer to c to find k. What else do we know? That we know when t equals 4, I believe. When t equals 4, the radius is 3. So when t equals 4, radius is 3. Plug that in now. So we have a third multiplied by r cubed. So that's a third 3 cubed equals minus k times 4 plus 125 over 3. From here, rewriting this. So 3 cubed is 27, divided by 3 is just 9. So we actually have that 9 is equal to minus 4k, just to make it look a bit nicer, plus 125 over 3. Taking away 125 over 3 from the left-hand side, because we're trying to find k, we have 9 minus 125 over 3. That would be equal to minus 4k, so we're going to divide the whole thing by minus 4, just to get it equal to k. Slap that into your calculator, we get 9 take away 125 over 3, and the answer divided by minus 4 gives us 49 over 6. So we get k to be 49 over 6. So now we have k and we have c, so we can put everything into our equation. So we have that 1/3 r cubed will be equal to, that's 49 over 6t, so that's minus 49 over 6t, and then it's going to be plus 125 over 3. And that is exactly it. That is our equation linking our radius and our time that they wanted. Okay, so for part B, we have to find the total time taken for the mint to completely dissolve. Give your answer in minutes and seconds to the nearest second. So remember, our time is in minutes, so we're going to eventually have to convert this into minutes and seconds to the nearest second. So first things first, we are finding the total time taken for the mint to completely dissolve. Completely dissolve, what does that mean? Well, completely dissolve means the radius will be equal to 0. So we have 0 cubed times a third, so we're going to have that 0 equals 49, or minus 49 over 6, minus 49 over 6 plus 125, sorry, t plus 125 over 3. So we have that 49, adding over 49 over 6 to the left-hand side, 49 over 6t equals 125 over 3. So we have that t equals 125 over 3 divided by 49 over 6, or multiplied by 6 over 49. Slap that in your calculator, we get t. Remember, t is in minutes, 2b. So we have 125 divided by 3 multiplied by 6 over 49. Be careful with your calculator not to make any silly mistakes. That is going to be 250 over 49, which equals, I recommend to write as many decimal places as you can, 5.10204, and a few more there. So what we're going to do is we want this to be in minutes and seconds. That is currently in minutes. We need it to also have in seconds. So how do they want it? They said very clearly they want it in minutes and to the nearest second. So we already have 5 minutes. So we have 5 minutes, and then to get seconds, we're going to have to do, take away 5 from our 5.10204. So answer, take away 5. That leaves you with the 0 point. So we have 0.1020408, so on. You take all those decimal places. That's going to be minutes. We have to times that by 60 to get it in seconds. To get it in seconds, that is going to be 6.122 seconds. To the nearest seconds, that is going to be 6 seconds. We have 5 mins and 6 seconds as our final answer. As our final answer to part B, 5 minutes and 6 seconds. Now moving on to part C, what do they want? They want a limitation of the model. Now this is just a logic question, one that people tend to struggle with. A limitation of the model. There are quite a few things you could say. You could say, for example, there's quite a few things, anything logical. For example, the mint won't, let's say, won't be sucked evenly. Won't be sucked evenly, so won't maintain that spherical shape, for example. It's kind of a weird question, I won't lie. Mint won't be sucked evenly, won't be spherical, won't remain spherical. You could also say, similar idea, the mint could break apart, for example, as you're sucking it. When you suck a mint, it normally breaks apart at some point. You could also say, another fun thing is unlikely to have constant sucking. Not sure if I should write that one down, but yeah, there's things you could say, but it's all about being logical. A great example would just be the mint won't be sucked evenly and won't remain spherical as you suck it and as you go on. So that is a limitation of the model. Yeah, definitely a interesting question. So on to number 11. Alright, question 11, partial fractions. We have 1 plus 11x minus 6x squared over x minus 3 multiplied by 1 minus 2x is equivalent to a plus b over x minus 3 plus c over 1 minus 2x. Find the values of the constants a, b, and c. Very formulaic, we're just going to multiply through by x minus 3 and 1 minus 2x. So on the left-hand side, we have, let's label this part A. So we have 1 plus 11x minus 6x squared. On the right-hand side, we're going to have, so multiplying through by x minus 3, 1 minus 2x, we're going to have x minus 3, 1 minus 2xa. Then we have plus b, or sorry, plus 1 minus 2xb, multiplying the whole thing through by 1 minus 2x and x minus 3. And that's going to be plus x minus 3c, okay? Just be very careful, make sure you write this bit correctly. So now we have to make appropriate substitutions of x into this to find the constants a, b, and c. So first things first, let's sub in x equals 3, because this will cancel out quite a few of our brackets. So x equals 3 on the left-hand side, we have 1 plus 11 times 3, take away 6 times 3 squared. This will be equal to, we can see we plug in x equals 3, this x minus 3, and this x minus 3 will both be equal to 0. So we are left with 1 minus 2xb, x is 3, so that's 1 minus 2 times 3, 1 minus 6b, 1 minus 6, that's going to be minus 5, minus 5b. So looking at the left-hand side here, 1 plus 11 times 3, this is 1 plus 33, take away 6 times 9, so take away 54 will be equal to minus 5b. So 1 plus 33 is 34, 34 minus 54, so we have minus 20 to be equal to minus 5b. We have b equals minus 20 divided by minus 5, b equals 4. So next value of x to plug in, to cancel out as many brackets as we can, is x equals a half. Because we can see when we plug in x equals a half, 1 minus 2 times a half is 1, so 1 minus 1 is 0. So all of these brackets will start cancelling out, which is perfect. So let's plug in now x equals a half. Plugging in x equals a half, we have 1 plus 11 times a half, 1 plus 11 times a half, take away 6 times a half squared on the left-hand side. This will be equal to, so once again, this 1 minus 2x will be equal to 0. So we're going to cancel our a's, cancel the b's, and we're just left with 1 half minus 3, so that's minus 2.5c. Minus 2.5c. So expanding out the left-hand side here, that's 1 plus 11 over 2, take away 6 over 4. So that's 1 plus 11 over 2 minus 6 over 4. Scrap it into your calculator. Don't do it in your head. You want to make sure you're getting these questions right in the exam. So we have that 5 equals minus 2.5c. So we have that c equals 5 divided by minus 2.5. So c equals minus 2. So we have b, we have c. To find a, we can actually sub anything as x. Just to make it a bit easier, let's sub in x equals 0. So on the left-hand side, we're going to have 1 plus 11 times 0. Take away 6 times 0, so that's just going to be 1. So subbing in x equals 0, we have 1 on the left. This will be equal to. So doing 0, once again, we know, or we don't know a, but we know b and c. So we have 0 minus 3 is just minus 3. 1 minus 2 times 0 is just 1 minus 0, so that's times by 1. Minus 3 times by 1 is just minus 3a. So we have minus 3a. Then we know that b equals 4. So what do we have? We have 1 minus 2x. X is 0, so that's 1 times b. So that's going to be plus 4. And then looking at c, we know c equals minus 2. So we have minus 2 multiplied by 0 minus 3. That's just minus 3. Minus 2 times minus 3 is plus 6. So what do we have? We have that 1 equals minus 3a plus 10. So we have that 9 equals, so take away the 1, then add over the 3a, so 9 equals 3a. So we have that a equals 3. So writing the full thing out, we have that 1 plus 11x minus 6x squared. It's always good to write the full thing out. 1 plus 11x minus 6x squared over x minus 3 multiplied by 1 minus 2x. I believe those were the correct things. 1 minus 2x, x minus 3. Exactly that will be equivalent to 3. So it was just a 3 plus, so what was b? We have b to be 4. So that's going to be plus 4 over x minus 3. X minus 3, and that's going to be take away, because c is minus 2, so over 1 minus 2x. So that's exactly what we have for part A. Minus 2 over 1 minus 2x for that c. Now moving on to part B, what do we have to do? So for part B, they want us to prove that f of x is a decreasing function. F of x being what we had in part A, that 1 plus 11x minus 6x squared over x minus 3 multiplied by 1 minus 2x. So first things first, we're going to have to write our function out as the partial fraction form, otherwise they wouldn't have asked us to find it. So we have 3 plus 4 over x minus 3, take away 2 over 1 minus 2x. Now when we're differentiating or integrating, we're going to want this to write it as to the power of something. In other words, this denominator, so x minus 3, we're going to write as 4 multiplied by x minus 3 to the power of minus 1, okay? So to find f of x, or to find f dash x, let's just quickly rewrite f of x to be 3 plus 4 multiplied by x minus 3 to the power of minus 1, take away 2 times 1 minus 2x to the power of minus 1. Why are we trying to find f dash x? Quickly just understanding why we're doing this. Decreasing function. Decreasing function means that f dash x will be less than 0 for all values of x, okay? So differentiating this, f dash x, the constant 3 will disappear. So then we have a little bit of chain rule. We have to bring that power down to the front and take 1 off the power. So that's going to be 4 times minus 1. That's going to be minus 4. We're going to have x minus 3 to the power of minus 2. We would also have to multiply by inside the bracket differentiated, but inside the bracket differentiated is just 1. And then we have minus 2 multiplied by minus 1, so that's going to be plus 2 times. And then we're also going to have to multiply by inside the brackets differentiated, so multiplying by minus 2, that's going to be multiplied by 1 minus 2x to the power of minus 2. So let's just rewrite this and make it look a little bit nicer. We have that f dash x equals minus 4 over, because it's to the power of minus 2, so it's the same as writing over x minus 3 squared. Then 2 times minus 2, so that's minus 4 over 1 minus 2x, also squared. Now, how can we say that f dash x is always less than 0? Well, here's what we know. We know 2 key important facts. X minus 3 squared and 1 minus 2x squared will always be positive. We know this because anything squared, so we can quickly say x minus 3 squared and 1 minus 2x squared must be larger than or equal to 0. Therefore, we have minus 4 over a positive number, no matter what x is, and we have minus 4 over a positive number or equal to 0, no matter what x is. So we can say, therefore, f dash x will be less than 0, or less than or equal. We can't divide by 0, so it actually have to be less than 0 for all values of x. Therefore, we can say that f of x is a decreasing function. And that is your answer to question, I believe we're on question 11. That is your answer to question 11. The partial fractions, nothing too bad. And then just a little bit of differentiation using pi. Okay, question 12, a little bit of trigonometry. We have to prove that 1 minus cos 2 theta is equivalent to tan theta sine 2 theta. So I'm going to start from the right-hand side here. Why am I starting from the right-hand side? Because I know there's multiple double angle IDs for cos 2 theta. I don't want to have to randomly pick which one to use. So we have on the right-hand side, tan theta multiplied by sine 2 theta. Let's get everything in terms of sine and cos. So tan theta is sine theta over cos theta. And then sine 2 theta is 2 sine theta cos theta. Okay, great. From here we can quickly see our cos thetas will cancel out. That leaves us with 2 sine squared theta. Now we can think about trying to connect it to the double angle ID. We know that cos 2 theta can be written as, connecting it to that 2 sine squared theta, can be written as 1 minus 2 sine squared theta. A little bit of rearranging. We have that 2 sine squared theta is equal to 1 minus cos 2 theta. Okay, perfect. So we can actually set our 2 sine squared theta to be equal to 1 minus cos 2 theta, and we've actually already shown, therefore, that the right-hand side, so we can say, therefore, the right-hand side is indeed equivalent to the left-hand side. And that's actually 3 marks very quickly. On to part B. Hence we're going to use the answer to part A, solve for x larger than minus pi over 2 and less than pi over 2, the equation sec squared x minus 5 multiplied by 1 minus cos 2x equals 3 tan squared x multiplied by sine 2x. So we're looking at our answer to part A and we know we're going to have to use it. So looking at our answer to part A, what can we quickly see? Well, we have 1 minus cos 2x. We know that 1 minus cos 2 theta is equivalent to tan theta sine 2 theta. Now we have x instead of theta, don't let it throw you off. So instead of that 1 minus cos 2x, we're actually going to sub in tan x sine 2x. So let's quickly write that all out. So for part B, we have sec squared x, I believe it's take away 5. So we have minus 5. This is going to be multiplied by tan x sine 2x, multiplied by tan x sine 2x using our answer to part A. And this will be equal to 3 tan squared x sine 2x. This is equal to 3 tan squared x sine 2x. Okay, great. So what can we do here? Well, I can quickly see we can actually divide through by tan x sine 2x. So dividing by tan x sine 2x, this leaves us with, on the left-hand side, sec squared x minus 5, and this will be equal to 3 tan x. However, key thing to remember, whenever we divide by a trigonometric function, we have to consider solution of whatever we just divided by being equal to 0. So we just divided by tan x sine 2x, and we have to consider the solution that this is equal to 0. The only way that we can have this is we can have tan x is equal to 0, or we can have that sine 2x is equal to 0, okay? But because of our restriction on our x's, they have to be larger than minus pi over 2 and less than pi over 2, because obviously the sine graph repeats and the tan graph repeats infinitely, so obviously there will be loads of solutions, but because we have this restriction, the only solution for x will be x equals 0. So we have the solution x equals 0 as our first solution. Let's try find the others right now. So we have sec squared x minus 5 equals 3 tan x. Let's try to get everything in terms of tan x. The reason I'm saying this is because we know there's a trigonometric identity that does indeed link sec squared x and tan squared x. We know that 1 plus tan squared x is equal to sec squared x. So what can we write down? Instead of sec squared x, we write down 1 plus tan squared x. So we have 1 plus tan squared x, take away 5 equals 3 tan x. Here we can actually set up a quadratic. So we have tan squared x minus 5 plus 1, so that's going to be minus 4, but then we can take away that 3 tan x. So we have 3 tan x minus 4 equals 0. So here we have a quadratic. Slap it into your calculator to solve your quadratic, and that gets you the solutions of, so we have 1 minus 3 minus 4. We get tan x to be equal to, two solutions here, so we have tan x equals to 4 and tan x equals minus 1. Tan x equals minus 1. Okay, so from here we're going to inverse tan minus 1 first, so we can actually take the inverse tan to find x. Inverse tan of minus 1 equals x. So first solution, we have that x equals, you could actually know your exact values. This is minus pi over 4. And then taking the inverse tan of 4, so we have that x equals inverse tan of 4. And this gives you an answer of, so how many decimal places do they want it? They want it to 3 decimal places. 3 decimal places. So find that inverse tan, make sure we're in radians again, of 4. This gives you 1.326. So we get 1.326. Now we know that tan repeats every pi. We can see if we were to add or take away pi from either of these solutions, we'd be outside of x larger than minus pi over 2 and less than pi over 2. So we actually have our 3 solutions out already. we have that x can be equal to 1.326 minus pi over 4, and we have, once again, equal to 0 because we divided by tan x sine 2x. So those are our three solutions to question 12 part B. And that's it, on to question 13. Alright, question 13, quite a long integration question. We're told that figure 2 shows a sketch of part of the curve C with equation y equals x ln x, x larger than 0. The line L is a normal to C at the point P, which has coordinates E, so this is the normal line, to the point P on the curve C, which has coordinates EE. The region of, shown shaded in figure 2, is bounded by the curve C and the line L and the x-axis. Okay, cool. Just explaining what we're seeing here. Show that the exact area of R is AE squared plus B, where A and B are rational numbers to be found. So integrating this, how are we going to go about it? Well, immediately I'm thinking we can't just integrate under a curve here to find the area. So we're going to actually split this integral. We're going to find the area under the curve, with upper limit here, a lower limit here. And we can also find the area of this triangle here. Now, this is a right angle triangle, so to find the area of the triangle, we can simply do half times the base times the height. Now we already know the height of this triangle to be E. How do we know it's E? Because we have the coordinates of P to be EE, and then we also know this x coordinate here will be E. But to find the total length of the base, we have to find this x coordinate here where the normal line crosses the x-axis. Because if we can find this x value, we can take it away from E to find the length of the base. So let's start going through it. To do this, we're going to need the normal equation. So let's go through it to find area of triangle. So area of triangle is half times base times the height. So we know the height is equal to E. Now we need normal equation. Okay, so that's what we're going to do. Find the normal equation. We already know that our normal line goes through the point EE. So this is already good. We know it goes through the point EE. Why is this good? Because we know that our straight line equation is y minus y1 equals m times x minus x1. So we already have x1 and y1, which is great. To find m, well, to find the gradient of the normal, this is going to be the negative reciprocal because it's perpendicular to our curve C at the point P. So what we need is the gradient of our curve C at the point P. Now we know our curve C has equation y equals x ln x. We are going to have to find dy dx, and then find the gradient at our point P. Okay, so finding dy dx, we have, so there's a bit of product rule, we leave differentiate, differentiate, leave. So we leave, differentiate, and then we add differentiate, leave. So that's going to be 1 times ln x. Okay, perfect. So this is exactly that we have dy dx to be equal to 1 plus ln x. Now we care about dy dx when we plug in e, so when x equals e. So we have 1 plus the natural log of e, which is just 1 plus 1, so it's going to be equal to 2. Therefore, m, the gradient of our normal equation, negative reciprocal, will be minus a half. Now plug everything in into our straight line equation. We have y minus y1, so that's y minus e, equals m, which is minus a half, multiplied by x minus e, because we had x1 to be e. Therefore, we have y minus e to be equal to minus a half x plus half e. Okay, this is great. So we have y equals minus a half x minus a half x plus 3 over 2, so that should e, plus 3 over 2 e. Perfect. So now what do we care about? We care about the value of x when y equals 0, because we cross the x-axis. So we set y equals to 0. Set y equals to 0. So we have that 0 equals minus a half x plus 3 over 2e. And then we have, adding over half x, so half x equals 3 over 2e. Multiply over 2, we have that x equals 3e. Okay, this is good. So we have our x coordinate over here to be 3e. Therefore, our base will be equal to 3e minus e. So we have that base equals 2e. So now we can actually just find the area of the triangle. Area of the triangle area equals our height, so h equals e, base equals 2e, so we do half, multiplied by e, multiplied by 2e, that just gets half times 2 is just 1, so that would be equal e squared. So we have e squared to be the area of the triangle. So that's one area that we're going to have to add on to the area under the curve. Now to find the area under the curve, we're going to have to use a definite integral. So we already know that the upper limit of this definite integral will be e, but we need to find the lower limit. So how do we find the lower limit? Well, we can see the lower limit is where our curve C crosses the x-axis. So we're going to set y equals x ln x. So we have curve C, which is y equals x ln x. We care about where this crosses the x-axis, so we set y equal to 0. So we have that 0 equals x ln x. Now remember, look back where we had our graph. We do not care about the solution of x equals 0. This is not the lower limit. We care about the other solution. So the other solution will be when ln x equals 0. So we care about where ln x equals 0. E both sides, so we have that x equals e to the power of 0. Therefore, we have that x equals 1. Okay, now we can set up our integral. So we have the definite integral, upper limit e, lower limit 1, of x ln x, integrating with respect to x, and then we're going to use integration by parts, or the faster way, which is ln e. Remember, we can't integrate the natural log of x, so we're going to be leaving and differentiating ln x. Remember, Liddy's leave, integrate, differentiate, integrate. Just a faster way than writing u's and v's, okay? So we're going to leave ln x, we have ln x, then we're going to have to integrate x, so that's going to be a half x squared. Then we have our limits of e and 1. We take away integral, definite integral, upper limit e, lower limit 0, differentiate, integrate. So differentiating ln x is just going to be 1 over x. That's going to be multiplied by a half x squared, same as before. I'm going to integrate that with respect to x. Okay, so on the left-hand side, let's just plug in the limits. So we have the natural log of e multiplied by a half e squared. Take away the natural log of 1 multiplied by a half 1 squared. Now, I'm actually going to delete everything we have on this natural log of one side. Why? Because we know the natural log of 1 is equal to 0. So we can actually ignore all of this. We can just draw a cross through it. So we have the natural log of e, so that's going to be 1 multiplied by half e squared. So that's half e squared. So we have half e squared, just writing that out very, very clearly. Half e squared, so we're going to be taking away definite integral upper limit e, lower limit 0 of, so now we have 1 over x multiplied by half x squared. We can see the x on the denominator will cancel out the squared, therefore we're left with half x. So integrating half x, that's all we have to do now. So we have half e squared, take away, integrating half x, raise that power up by 1, divide by the new power. So we're going to have a quarter x squared. Once again, upper limit e, lower limit 1. So now we just have to plug in e and 1. So we have half e squared, take away, plugging in that upper limit of e. So that's going to be a quarter e squared, take away quarter times 1. So take away a quarter. Okay. So we have half e squared. Actually, let's do it all at once. So we have half e squared minus a quarter e squared. So that's just going to be a quarter e squared minus a quarter. So that's going to be plus a quarter. So this will actually be the area under the curve. Now to find the total area, we have to add the area under the triangle, under the area, or plus the area under the curve. So what do we have? We have e squared to be the area of the triangle. So exactly that, we have area triangle. Oh, that's not a good triangle. Area triangle plus area curve, okay? So we have e squared, which is the area under the triangle, plus a quarter e squared plus a quarter, okay? So that will get us 5 over 4 e squared plus a quarter to be the total area. Is that in the form they wanted? They wanted it in the form of ae squared plus b, where a and b are rational numbers to be found. So therefore, we have a to be 5 over 4 and b to be a quarter as your total area. That's your final answer to question 13. On to 14. Okay, last question of the paper. Question 14. A scientist is studying a population of mice on an island. The number of mice n in the population, t months after the start of the study, is modeled by the equation n equals 900 over 3 plus 7 times e to the minus 0.25t. Part A, nothing tricky. We just have to find the number of mice in the population at the start of the study. So start of the study, t is equal to 0. T is equal to 0, so we have 900 over 3 plus 7 times e to the power of 0. Why is it to the power of 0? Because we have minus 0.25 times 0. We know anything to the power of 0 equals 1, so this will simply be 900 over, so that's 3 plus 7 times 1, so that's going to be 900 over 10, which will be equal to 90. So we have 90 mice at the start of the study. Now moving on to part B. Part B is definitely a tricky question. Part B, we have to show the rate of growth, dn dt, is given by dn dt equals n times 300 minus n over 1200. So first things first, let's find dn dt. So we know that n equals, just rewriting what they give us in the question, n equals 900 over 3 plus 7 e to the minus 0.25t. So we want to find dn dt. We have a fraction. I think the easiest way to do this will be using quotient rule. So reminding ourselves of quotient rule, we have v multiplied by u dash, take away u multiplied by v dash, all over v squared. Okay, so we know that u is our numerator, so u equals 900. U dash, differentiating a constant, it disappears, so that will just be equal to 0. We have that v equals 3 plus 7 times e to the minus 0.25t. Differentiating this, so 3 is a constant, disappears, and then we have, so we're going to multiply this by what we have in the power of v differentiated. So differentiating minus 0.25t would just be minus 0.25. That's the same as minus a quarter. So we have minus a quarter multiplied by 7 times e to the minus 0.25t. Okay, great. From here, let's plug everything in. Now we can actually see when doing v multiplied by u dash is equal to 0. So this will all be equal to 0. So we actually have 0. Take away u times v dash, so that's going to be 900 multiplied by v dash, so that's minus a quarter, multiplied by 7 times e to the minus 0.25t. That's going to be all over v squared. So v squared is just going to be 3 plus 7e to the minus 0.25t, and all of that will be squared. Okay, let's tidy this up a little bit. So what am I going to do? I'm going to do two things. This minus a quarter I'm going to bring to the bottom of the fraction, and we actually have minus a quarter. Okay, perfect. So what can we do? We can rewrite this as 900. So dn dt, just making this very clear, dn dt will be equal to 900 multiplied by 7 times e to the minus 0.25t. We're going to bring that a quarter down to the denominator, because remember we had that minus as well, so we can just leave it as a positive. So this will all be over 4 times, and I'm actually going to rewrite this 3 plus 7 times e to the minus 0.25t squared as 2 separate brackets, okay? You'll see why I'm doing this later. So we have 3 plus 7 times e to the minus 0.25t. I'm going to just write this bracket out twice. So that's 3 plus 7 times e to the minus 0.25t. So this is actually what we have to be dn dt. But here's the problem. This would be 2 marks. In the show that question, we have to show that it equals n times 300 minus n over 1200. Currently, we only have everything in terms of t. So let's remind ourselves, we're going to write a little box on the side here, reminding ourselves of substitutions that we could potentially make to put n into this dn dt equation. So we have that n equals 900 over 3 plus 7 times e to the minus 0.25t. So what are we trying to get rid of? Well, we also have this 7 multiplied by e to the minus 0.25t in the numerator, and then we have 3 plus 7 times e to the minus 0.25t in the denominator as well. So we can actually make that the subject. So we have that 3 plus 7e to the minus 0.25t is equal to 900 over n. Okay, that's useful. And then we also have just kind of seeing everything that we may potentially have to substitute. So there should be a t here. This will be equal to 900 over n. That is going to be take away 3. Okay, so that's all the useful substitutions that we can use in the question. So let's kind of go through substituting. Now we can actually already spot that we can actually make a substitution for n. We can see this 900 over 3 plus 7e to the minus 0.25t is actually n itself. So we can already write in n for that. Being very careful when we make these substitutions. So we actually have n. Then what do we have left? We have multiplied by 7e to minus 0.25t. I'm going to do this slowly and clearly just to make sure everything makes sense. So we have 4, then we still have that 3 plus 7e to the minus 0.25t. This is why I wrote the brackets out separately. So we've actually got rid of 1 already. So what do we have left? We can actually make the 2 other substitutions. So we know that 7 times e to the minus 0.25t is that 900 over n minus 3, and that 3 plus 7e to the minus 0.25t will be equal to 900 over n. So let's just make those substitutions in. So we have that. We have n times, actually let's just write it as a bracket. We have n multiplied by 900 over n, take away 3 in that numerator, and then in the denominator, we have 4 times, so 3 plus 7e to the minus 0.25t, that's going to be 4 times 900 over n, okay? So at this point, we can already start comparing to what we're trying to get to. We're trying to get to n times 300 minus n over 1200. So first things first, let's just expand these brackets. On the numerator, we have 900 minus 3n, and that's going to be over, we can do 4 times 900, that's going to be 3600 over n, okay? First, we don't have any n in the denominator on what we're trying to get to, so let's multiply the bottom and the top by n. Multiplying the bottom and the top by n, we have 900n minus 3n squared all over 3600. And we can also see we have 1200 on the denominator and we have 300 on the numerator. So let's divide the top and the bottom. Divide the top and the bottom by 3. Remember, when we do something to the top and the bottom, we're not changing the fraction. So we get 300n minus, dividing by 3 is just going to be minus n squared all over 1200. Okay, great. So now, last step, all we have to do now is factor out that n from the numerator, and then we're there. So we have, factoring out that n, this would be n multiplied by 300 minus n all over 1200. And once again, just reminding that is equal to dn dt by using the appropriate substitutions. So quite a lot of algebra, quite a lot of manipulation. You could have gone about it slightly different ways, but you'll eventually get to the right answer depending on the substitutions you make first. But yeah, that is your answer to part B. Okay, so moving on to part C, we're told the rate of growth is at a maximum of the t months. Find, according to the model, the value of t. So we have to find when dn dt is at its maximum. So what do we know? Well, we know, just from before, that dn dt is equal to n times 300 minus n over 1200. So you could actually use this. If you couldn't get the previous answer, you could use what they give you. So we actually can't find t when dn dt is at its maximum, but we can find n. So to quickly sketch this out, we can see this is going to be a negative quadratic, minus n times n, it's going to be minus n squared, so it's going to have that frowny face shape. We also know it's going to have roots at 0 and 300, just looking at the numerator here. So we can draw this frowny face negative quadratic. We know it has roots at 300 and 0. So then from here, we can actually see it's going to reach its maximum because it's a negative quadratic. It's going to be symmetric. So it reaches its maximum halfway between 0 and 300. So n equals 150. So dn dt reaches its maximum at n equals 150. Now we have to find the corresponding value of t. Well, we know that n equals 900 over 3 plus 7e to the minus 0.25t. So plug in n equals 150 into this equation and rearrange for t. So we do 150 equals 900 over 3 plus 7e to the minus 0.25t. We are trying to make t the subject of the formula. So we can rewrite this, multiply over by 3 plus 7e to the minus 0.25t, divide over by 150. So we have that 3 plus 7e to the minus 0.25t will be equal to 900 divided by 150. That'll be equal to 6. Okay, so from here, what we can do is we can have 7e to the minus 0.25t equals 6 take away 3 will be equal to 3. We can now divide over by 7. So we have that e to the minus 0.25t will be equal to 3 over 7. Get rid of that e, take the natural log of both sides. So we have that minus 0.25t will be equal to, just all this rearranging here, will be equal to the natural log of 3 over 7. From here, we can divide by minus 0.25. Dividing by minus 0.25 is the same as multiplying by minus 4. So we have that t equals minus 4 multiplied by the natural log of 3 over 7. Slap this into your calculator to get your final answer. So we have minus 4 multiplied by the natural log of 3 over 7. And that will give us an answer of, for t, capital T, to be 3.39 months. This will be 3.39 months to 3 significant figures. And that's your answer to part C. Now we're going to move on to part D. So part D, they like to do these kind of questions at the end. Part D, they want us, according to the model, the maximum number of mice on the island is P. So the maximum number of mice, state the value of P. Okay. So what do we know? Once again, just rewrite your original equation. We know that the number of mice equals 900 over 3 plus 7 times e to the minus 0.25t. Okay, so we're trying to find the maximum number of n. So the thing we have to realize is we have 900 divided by our denominator. To get the maximum possible number, we're going to have to divide by the smallest possible number. Okay, so what do we want to do? We want to divide by smallest possible number. Okay, to get the maximum number of mice. Okay, so the smallest possible number will be 7e to the minus 0.25t. We can actually know this if we quickly draw out our e to the x graph, just to make this really, really clear. If we have e to the power of a very, very negative number, it will actually tend towards 0. So we can say as t tends towards infinity, e to the minus 0.25t, because think about it, we're going to have minus 0.25 times by a really positive number. That means we're going to get a really, really negative number. Looking at the graph, this means we're going to get e to the power of this really negative number. This will tend towards 0. So as t tends to infinity, e to the minus 0.25t does indeed tend to 0. You can actually write 7 times e to the minus 0.25t, because something that tends towards 0 times by 7 still is tending towards 0. So this means we actually tend towards 900 over 3, which would be equal to 300. So the mark scheme does actually allow your maximum number of mice, so your max n to be 300, but we won't actually quite get to 300, so the correct answer here is the maximum number of n will be 299, because we won't quite get to 300 mice, because we never actually reach so e to the power of minus 0.25 times that really large t number will never quite reach 0, so we won't quite reach 300. So the maximum number of mice will be 299 mice. That is your final answer. 300 is accepted. That is 2018 paper 2. With these kind of questions, they love it when you have e to like a really negative number tending towards 0. They do enjoy these kind of things. But that is it. 2018 paper 2.